Hello and welcome to this Introduction to nRF Connect SDK webinar, Cellular IoT Made Easy. This webinar should take approximately 45 minutes, including a demo and a Q&A at the end. I'm your host today. My name is Bjorn Kvale. I'm a product marketing engineer with a Master of Science degree in Engineering, Cybernetics, and Robotics from the NTNU in Trondheim, Norway. I have 2 years of experience working in the tech support group at Nordic Semiconductor. So if you're familiar with Nordic, you've probably checked out our dev zone or even asked a question on our dev zone. And it's people like me that will help answer your cases along with the community, of course. I mainly focused on software-related support cases with a large focus on both Bluetooth Mesh and later the nRF 91 series. Like I said, the webinar should take approximately 45 minutes. Questions are definitely encouraged. And you should see in the webinar tool we're using, you should see a questions bar on the right-hand side. So if you click on the questions tab, then you can ask your question there and we will see it. The questions are anonymously posted and we'll do our best to answer all of the questions at the end of the webinar. So we won't be taking questions during the webinar, but we'll take a look at all the questions at the end. And we'll also share a Q&A after the webinar with any updated answers if that is necessary. Content-wise, first I'll give a short intro about what the nRF Connect SDK is, along with a short intro to real-time operating systems. And then after that, we'll get started with setting up and configuring nRF Connect SDK, including an overview of what is included in the nRF Connect platform itself. So you do get free Sega Embedded Studio support. So if you do use the nRF 91, you are able to use this great IDE for free. And last but not least, there's support for desktop and cloud apps, which I'll discuss later. Here in the figure on the right-hand side, you can see some blue rectangles and some green rectangles. The green rectangles signify open source modules. So you can see the Zephyr kernel and middleware, including the IP protocols that are supported by Zephyr, in addition to memory management, DFU, via the MCU bootloader. On the top, you can see the application frameworks, reference designs. So that would include the different examples we have, whether that be AT client, HTTP update, asset tracking, etc. Reference designs, we do have the Thingy 91. If you haven't seen that webinar yet, it is available on our YouTube account. And on the bottom there, you can see the Nordic low-layer firmware, including root of trust bootloader, the secure domain architecture with secure and non-secure regions of flash. You have the MAC layers, so BSD, which I'll discuss a bit later. And we do also have support for Bluetooth Low Energy, 802.15.04, Zigbee Thread. Drivers, we include NFC, crypto, SPI, UART, USB, etc. So if you're used to our nRF 5 platform on the nRF 51, nRF 52 series, we do support a lot of the same drivers and examples in nRF Connect SDK. But of course, the nRF Connect SDK is for the nRF 91 series. If you are still using nRF 52, we recommend using the nRF 5 SDK. Moving on to software architecture. So as you can see here, the nRF Connect SDK is running on the application processor side. Of course, you have the user application along with the application layer IP stack. So whether that be CoAP, MQTT, HTTP, lightweight machine-to-machine, etc. And then we use the secure BSD socket API. So the BSD layer is then used to communicate between the application processor and the modem processor. So those are two Cortex M33s running. On the modem side, then you have the IPv4, IPv6, TCP, UDP, TLS, DTLS layer, along with the LT stack themselves, so the L2, L3 layer. Connectivity, and we of course have connectivity in application software. We also have support for over-the-air modem and application updates. And of course the reference design, the Thingy 91, which was mentioned, does have multiple sensors, and those are all supported. If you want support for thin modem operation, that is possible. So by thin modem, we basically mean using the nRF 91 chip as a connectivity chip instead. And then using a different application processor, that is possible if you wish to do so. A quick intro to a real-time operating system. Essentially, the goal is to ensure predictable and deterministic execution pattern. So you want threads, you want them to finish at a set time, basically. Embedded systems often have strict timing requirements, so you need to get done with tasks after a certain amount of time. And the way you achieve this is the scheduler decides which task to execute at which time based on setting priorities of different tasks. So each execution thread is set a priority. And I won't go into too much detail here, but you can see the Zephyr kernel here. You have task management, synchronization, memory management, timer management, and of course interrupt event handling is very important, and also device I/O management. So why bother using an open source RTOS? We do see there's a trend going towards open RTOSs for MCUs in IoT, whether that be Zephyr project, Minute, Contiki, ARM Embed, FreeRTOS. There's a greater number of open standards in applications. It doesn't necessarily mean that vendor implementations are better. They're just slightly different. Of course, it helps that you do have free use and distribution. The price is right with open source. And you also do have very good security and stability. So it is a proven success with the open review and also open information sharing, as we can see with Linux, for example. There is also a lot of great third-party expertise that's developed around open source software. So why did we decide to focus on the Zephyr RTOS? One of the main reasons is that Zephyr was designed and built for low-power wireless, and low-power wireless is a part of our DNA. So first with the BLE chips that we've become quite well known for, and now also on the nRF 91 side, we want to show that low power design on the nRF 91, and we believe the Zephyr project really complements that, our hardware design on the nRF 91 series. Zephyr is independent from the Linux Foundation project. It is also very scalable, which is very useful. So you do have anything from very small configurations for memory-constrained devices, but also powerful and feature-rich. So if you do need a more complex application, you have configurations for large memory and also high processing power devices. Also, Zephyr does include all of the popular IP standards. So we like to call that vanilla code, since those IP standards that software has been tested and proven, that lets us focus on other important features such as firmware over-the-air updates, for example. Right, and this is very similar if you look at our, let's say, our Bluetooth mesh solution. There we do have a lot of proprietary features that some other competitors might not have. We have been project members of the Zephyr since 2016. We plan on continuing to work with Zephyr to ensure best-in-class features and performance. Let's move on to getting and using the nRF Connect SDK. Like mentioned before, it is hosted on GitHub and supported by Git version control and also West. West is essentially a Swiss Army knife sort of tool. It's a command line tool which you can use for both programming and flashing if you wish to use that instead of Sega Embedded Studio, for example. It also provides multiple repository management support. It's similar to Git to a certain extent, more specialized to be used for Zephyr and nRF Connect SDK. All of the code does come pre-integrated in one SDK, and you can also fork the nRF Connect SDK code and contribute to the SDK if you wish to do so. It also does allow syncing of nRF Connect SDK code for use in private repositories, right? So if you do have some sensitive code that you don't want to share with the world, we understand that, you are able to do that too in your own private repository. So let's move on to setting up the toolchain. What you basically do, you download nRF Connect for desktop, and then you download the SDK version using the Getting Started Assistant app. Now here, so you can see a quick screenshot of that app, and there you can see install the toolchain, then you clone the nRF Connect SDK, download Sega Embedded Studio, and also set up a project in Sega Embedded Studio. Sega Embedded Studio does get updated every once in a while, so here you can always find in step 3, you can always find the latest download link. And we do have platform-dependent guides on this app, so they might look slightly different depending on whether you're using Windows, Mac OS, or Linux. And of course, all of these apps have been tested on all 3 of these platforms. Like I said, we do use Sega Embedded Studio to configure, build, and debug. You can then select which SDK features you want to auto-include, add your code, and then you can also add configurations for your product PCB. There are 4 main repositories, 4 main folders. So that is the nRF Connect SDK, you have nRF xlib, Zephyr, and MCU boot. And we haven't called our folder, we have just called our folder nRF. It's not called nRF Connect SDK, but that's basically the nRF folder is where we have most of our application code. Yep, and then of course you have nRF xlib, Zephyr, MCU boot. You basically fork the nRF repository into its own branch, and then you update the nRF repository using Git. The project repositories are then updated using the West tool. So getting and using nRF Connect SDK, as you can see, the first thing you do then, once you've opened up the Sega Embedded Studio, you go to Tools, Options, and then you make sure that the GNU ARM Mbed toolchain is set correctly. You want to use the version 7 2018 Q2 that is specified in the Getting Started app. The Zephyr base directory you want to set to your Zephyr folder. So that's inside NCS and then the Zephyr repository. Moving on, then you go to File, Open nRF Connect SDK project. So in this example here, we're opening up the AT client, where you can send AT commands to the nRF 91. Make sure the board directory is set correctly, so that's in the Zephyr folder, and you want to use the nRF 9160 PCA 10090. The board name, it's very important to use the non-secure version of the board on the AT client application because it is using the non-secure part of Flash. And last but not least, you have the build directory, which you normally just set right under the AT client folder. And you can call the build folder whatever you want. So in this example here, we are using the version 1.0.0 tag, which is the latest sort of tagged release which is, I guess, optimized. It's fully tested, so it's a stable release in essence. Here we can see just the latest tagged releases. So as you can see, on May 10th we had the version 0.40, and on July 3rd it's the version 1.0.0. So you do want to start with a tagged release to ensure higher quality assurance. And here on these links, we will provide these links. You can actually see this exact screenshot, and we do also have additional documentation. The current CEST release is version 420A. Project configurations are controlled through Kconfig and DTS. Kconfig is Zephyr kernel configuration, and DTS is the device tree. So to configure a project, you go to Project, Configure RF Connect SDK project using menu config, which I'll explain in the next slide. And then to configure the device you just go to Project, Edit Device Tree. So what you do is you go to Project, Configure RF Connect SDK project, and then you can choose menu config, whether you want to use change the menu configuration for the Secure Partition Manager on the bottom, for the MCU bootloader if you're using that, or the menu config of the app itself that you're running. So in this example, the AT client application. You have the search field up there, and you can then check and uncheck different features that you want to use. It's very, very easy to use. So in this example, we are enabling AT commands because that's the whole point of this example. Here we can see the device tree properties. So this is then used for changing the pin layouts if you wish to do so. So again, you go to Project, Edit Device Tree, and then here we can see you can search for UART if you wish to do so, and here you can see the UART pins that are used. So TX, RX, RTS, CTS, and you can see the values that they're given. And the same for SPI, the UART 1, 2, 3, etc. Now, moving on to the nRF Connect family, you do have the nRF Connect SDK, which I've talked quite a lot about with the different examples, application protocols, the Zephyr RTOS, different libraries we have, and also hardware drivers. Then we've talked a bit about the nRF Connect for desktop, the Getting Started Assistant app. We do have a programmer app, LT Link Monitor, Trace Collector. I won't talk too much in detail on those. We might do some later videos on that. And then we also have the nRF Connect for Cloud. So we do have some examples there. We have device management and also SIM management on nRF Connect for Cloud. It's very simple for you as a developer to then prototype using nRF Connect SDK, using our solution here. So here are just some of the examples. In the nRF Connect SDK, we do have an asset tracker example. That's the example that's shipped on the Thingy 91, if you have one. We also have an LTE sensor gateway, where you're using an nRF 91 DK as a sort of gateway between a Thingy 52 or any other Bluetooth device. And then you use the nRF 91 as a gateway to the cloud. The AT client example, which lets you send AT commands. You can, of course, also send AT commands in the asset tracker example. We do have a simple MQTT for getting started with MQTT. CoAP 2, lightweight machine-to-machine, HTTP application update for a firmware over-the-air update of your application. We also do have Amazon Web Services photo sample, Secure Services sample, and also the Secure Partition Manager. The reason this one's italic is because the Secure Partition Manager is required by all code. It sets up the non-secure and secure regions of Flash and the peripherals. But I'll go through that in the next slide. So here you can see on the diagram on the right-hand side, you can see you have the secure part of Flash and the non-secure part of Flash. So the secure boot is run on the secure part, and then on the non-secure side you have the application code and also the BSD socket, which is used to communicate to the LTE modem. So this is the top rectangle is the application processor, and the bottom rectangle, the dark blue rectangle, is the modem processor. So basically what you're doing, you're configuring the system protection unit, and then you're jumping to the application. That's what the Secure Partition Manager example does. There's no DFU. On the secure side, the CPU thinks that the executed code is secure, so there's no restrictions there. You can use the ARM crypto cell, for example, which is essentially a hardware accelerator for security applications for cryptography on resource-constrained devices, on low-power devices such as the nRF 91. But I won't go into too much detail on the ARM crypto cell. But it's worthwhile to know that you do have a crypto cell on the nRF 91 series. And then, of course, you have the non-secure part of Flash, where the CPU thinks the executed code is not secure. So there are some restrictions there, and the modem actually only works in this mode. So you need to be able to use the non-secure part to talk to the LTE modem. And of course, you also set up all of the peripherals too. So if you want to use UART 0, 1, or 2, they need to be defined in the SPM, in the Secure Partition Manager example, before you can use them in your application. Like I said here you can see a little snippet on the right-hand side where the UART 1, 2 are set up, in addition to timers, SPI, TWI, etc. And of course, the peripherals do need to be non-secure in order for the application to use them, since the application is running in the non-secure domain. Moving on to the asset tracker example. The asset tracker example sends real GPS coordinates, accelerometer, temperature, humidity, and air pressure data to nRF Connect for cloud. So as you can see in the figure below, using the Thingy91 as the MQTT client, and then you communicate via LTE, so via TCP to the LTE base station, to the cloud, to the internet, and then to the nRF Connect for cloud. And basically the way this works is, the way we've set this up is you need to be in a power saving mode to be able to activate the GPS. So to be able to have concurrent LTE and GPS, the LTE connection needs to be in a power saving mode, so very low power mode, which then allows the GPS to run for, let's say, 360 seconds. Then it gets a GPS coordinate, and then you reconnect to the base station and send the GPS coordinate in addition to accelerometer, temperature, humidity, and air pressure data. And then you repeat that process. You go back into a power saving mode, which lets the GPS run for a bit, and then you turn on the LTE link again and send all the rest of your data too. And of course, the source code is available for connecting to the server, and you can also see all of the data in the nRF Connect for cloud. If you haven't seen the Thingy91 webinar yet, I would definitely recommend looking at that. Especially also the last 5 or 10 minutes. That's where we show the demo of this application. Yeah, so the nRF Connect SDK, you do have the different application protocols: MQTT, CoAP, HTTP, lightweight machine to machine. Includes the Zephyr RTOS, also the different hardware drivers: GPIO, I2S, SADC timer, UART, watchdog timer, etc. And now on to the nRF Connect for cloud part of our platform. We do have, like I said, the asset tracker does display GPS coordinates on the map and switches a state. We also have the LTE sensor gateway, which displays sensor data from the Thingy52. So that's the one that uses Bluetooth, not LTE. And the nRF 9160 DK management too. So you can connect different devices, and then you can see the IMEI code on the nRF Connect for Cloud platform. We also do have SIM card activation for the iBasis SIM cards that are shipped with the nRF 9160 DK and the nRF and the Thingy91. Great, so that was the introduction to the nRF Connect SDK, Cellular IoT Made Easy. I hope you enjoyed it, and now we'll go over to a demo and the live Q&A. Thank you for listening.
So when you first open up nRF Connect for desktop, what you'll see is, as I've already installed some apps, but first you'll need to install some of these apps. Then you open up the Getting Started Assistant, open there. And then as you can see here, you have a quick overview. Installing the toolchain. We use something called Chocolatey to install most of the toolchain, and it works very well whether you're using Windows, Mac, or Linux. It works quite well. So you want to install Git, Python, Ninja, etc. As you can see here, you want to set the GNU ARM embed path too afterwards, and also the source code root to verify some of these tests, and also the Chocolatey installer, in addition to the NCS tag that you're currently running. Next step is to clone the nRF Connect SDK. So you want to download the West tool. After that, you want to make an NCS folder, initialize the nRF repository, and then run an update on the nRF repository. And here, with the git checkout command, you can actually check out which tag you want to use. If you use a git bash, you can actually tab in which NCS tag you want to use. So I would recommend using git bash. And then of course afterwards you need to update to be able to use that branch. And last but not least, once you've checked out the tag, I would just go with the latest checked tags, version 1.0.0 tag. And then here you can see you need to run some requirement scripts. Next, you want to download Segra Embedded Studio. These links do get updated every once in a while. If you've seen on DevZone somewhere that there's a new Segra Embedded Studio out, you can definitely download it here from this link. And last but not least, setting up a project. I'll go through this afterwards. Tools options, you want to set up the Zephyr base, the GNU ARM embed toolchain directory, in addition to CMakes, the board directory, board name, board directory, and if you want to delete the existing CMake cache, you can do that. And last but not least, you just press OK. As you can see, once you open up Segra Embedded Studio, what you then can do, you go to Tools, Options, go down to nRF Connect here, and then as you can see the GNU ARM embed, this is where that is located, the GNU ARM embed tools, and then the Zephyr base. Right now I'm on the master branch, but of course you can use whichever branch you want, and it's pointing to the Zephyr repository. And I press OK there, then you just do File, Open nRF Connect SDK project. As you can see, we're on the master branch here, asset tracker, the board directory. I'll change this. This is actually pointing to the Thingy91 right now, but what we want to do, we'll do the standard. It's ARM, RF9160. There. So that's the folder we want to use there. And the board name, since this is the asset tracker, it's running on the non-secure part of Flash. So that's why we use the NS version of the board name. And the build folder, you can call it one. You may want to clean the build directory too. And then it takes a bit of time, and then it's basically ready to run.